Greetings, folks. Professor Fiore here, and this is going to be part one of a two-part sequence on how to use a simulator to create three-phase simulations, three-phase power systems. Now, you might have a simulator that does not have built into it a three-phase generator. No problem. Now, there are a couple of tricky bits. There are some gotchas. It all depends on the kind of simulator that you're using. But I'm going to go through all this and show you how you can use pretty much any simulator. Even if it doesn't have a three-phase generator, you can still do three-phase simulations. So I'm going to use Tina TI here. There's some unique little things here. But like I said, with slight modifications, you'll be able to use pretty much any generator, even if it doesn't have, any simulator, even if it doesn't have a three-phase generator. All right, so what are we looking at? Well, we're looking at four possibilities, right? So if you haven't seen the videos on three-phase systems, I strongly suggest you look at those, look at the associated material in the textbooks before you go through this, otherwise it could be a little confusing. But assuming you have, you know that there are four different kinds of configurations. We can have a wye-connected generator or a delta-connected generator, and the loads can be either wye-connected or delta-connected. So you have four possibilities, right? Wye-connected generator, wye-connected load, wye-connected generator with a delta-connected load. That's what we're going to look at in part one in this video. And then in part two, we're going to do the other two, a delta-connected generator with a Y load, delta-connected generator with a delta load, all right? So things we have to concern ourselves as far as the simulator is concerned. Number one, RMS versus peak voltages. Power systems are almost always, well, I should say virtually always, specified in terms of RMS values, right? But some simulators, for example, Tina, likes to set up the generators with peak voltages, and that makes perfect sense for signal sources, right? So that's one thing. The other really big thing is guaranteeing that you have the proper generator phases, right? So we have a normal three-phase systems. There's a 120-degree phase shift between the three legs, right? Another possible issue is the issue of ground. Some simulators will not simulate unless you have a ground. And if you've dealt with something like maybe a delta-delta system, you don't necessarily have to have a ground. And finally, there's the possibility of the generators being shorted. And this is an issue with delta-connected systems. In other words, the internal impedance is assumed to be zero. So when you have a delta configuration, you can wind up with a system where the other phases, the other legs, the other generators are effectively shorted when you do an analysis of that. So we want to look at all of those things. Okay, great. Now, we start with the idea of an AC generator. I am going to need three discrete generators. So, in Tina, I can come up here and just, grab my voltage source, right, which I've already done over here. So I've pulled down three generators. Now I'm going to use standard North American power, which is 120 volts RMS at 60 hertz. Feel free to change these depending on where you are. If you're in Europe, most of Asia, Australia, certain parts of South America, you're going to be looking at a 50 hertz system, probably 230 volts, maybe 220, maybe 240, all right? There are some other parts in the world where we might see a 230 volt 60 hertz system or a 110 volt 50 hertz system. So you just set these up for what you need. So I'm just going to grab voltage generator number one over here. And of course, we would have to set this to sine wave. Hit the ellipsis, and you can get your properties. So as I said, Tina likes to set things up for peak amplitudes. So I've selected a sine wave, and the peak amplitude over here, right, 120 volts RMS, you would multiply, of course, by the square root of 2, roughly 1.414, and you get about 170, a little bit more accurately, 169.7 volts peak. So set that up, and then, of course, your frequency, like I said, I'm using North American standard power, so that would be 60 hertz. Okay, great. Now, you go along and you do that with the other ones with a little bit of a wrinkle. All right, so here's generator 2. I come in here, same thing, 169.7, 60 hertz. However, I do want to throw in a value for the phase, right? So this is phase relative. So this is going to be relative to generator 1. Now the 3 phases all have to be 120 degrees apart. So the second phase is going to be 120 because the first one was set to 0. And then when we go into the third generator, all right, it's going to be 120 shifted another 120 or 240, right? And then if you do another 120, you're back to 360 or 0. Okay, so those are your 3 generators. Now, this is the first gotcha that people kind of screw up on, if you will. You know, if you're going to do a wye-connected system, people will take this one, they'll put it down here, and they'll connect these 3 things together, all right? And they say, okay, so now I got my 3 phases, phase 1, phase 2, phase 3. Well, if you look carefully at this, you realize this is a major error, major error. Because look at the reference polarity for generator 3. That's a plus up here, right? That's the plus going to your common point. So you've actually thrown in an extra 180 degrees. So this was 240, right? Plus the 180. Well, sorry, not what we want to do. How do you really want to do this? Now, there's no law that says you have to set it up in a Y configuration, but if you do, right, you know, what you want to do is rotate this, okay? So that you have something like this. Now you can go in and you can connect these up so it looks like, you know, a Y, a T, okay? Now you have your 3 phases. So what I always recommend you do is think, and you're going to see this again and again when we talk about loads and delta configurations and so forth, think in terms of this little sort of circular clockwise motion around a center point. So as you're going on the outside here, it's plus, plus, plus. That's what you want to see, plus, plus, plus as you're going around, okay? All right, so that's how we would configure this, and I would have my 3 lines coming out. So the first thing we're going to look at is a YY system. In other words, a Y-connected generator and a Y-connected load, all right? So here we go. So again, notice the pluses that we have, how this all goes around. Now, in this system, YY system, you can have a central ground, right? This is one of the other issues that we were talking about. Some simulators, they won't simulate unless you have a ground. Tina isn't like that. You don't have to have a ground. You know, as long as you're doing all relative measurements like I am here with these voltages here, no sweat. These, on the other hand, are relative to ground. So you do have to have a true ground. But, you know, there's no big deal here. I mean, if this was a delta connected load, you could just tack a ground on here and you have your delta connected load. It doesn't really mean anything, but it would allow the simulation to work. All right. Typically, though, for things like this, you would probably want to use voltmeters rather than Tina's you know, voltage point probe sort of thing that they have here. But either way, in this particular case, it's going to work fine. In some future examples, I'll just be using voltmeters right across these elements. But either way will work, right? So you know, all depending on the simulator, you probably either have something like this or a virtual voltmeter that you can stick out there so it's floating. It doesn't have to go back to ground. All right, so here we go. Right, here's our basic YY configuration. It's the easiest one. It's the most straightforward one. It's really just 3 circuits if you think about it. You know, if I was looking at phase 1 over here, you know, this comes out, goes through, you know, load number 1, if you will, R1, which goes back to our ground. So you really have like 3 circuits. You know, VG2 drives R2 and VG3 drives R3 and happy, happy, happy. Okay, so it's kind of easy to figure out if you're going to figure out powers and stuff. Or you want to see, we're going to do a transient analysis. So obviously we're going to see peak voltages. This is another one of those issues. So the peak, right, 120 volts peak, like we said, is just a smidge under 170 volts. So if I want to figure out what the currents are, you know, I would take that 170-ish volts, divide by the 10 ohms, and we'd be looking at about 17 amps of current flowing through each one of these legs. All right, great. Now, let's turn our attention to the line voltage. So remember, the line voltage is from one of these output conductors, one of the phases, to another. So the first one would be phase 1 to phase 2, right? Generator 1 to generator 2. So that's this one up here I call V line number 1. Notice the polarities on here, right? Here's positive going to VG1, the negative goes to VG2. So that's what I'm looking at, VG1 relative to VG2. So here again, here's this idea of going around this little clockwise kind of thing. So for VG2 to VG3, this one, V line 2, it's going to be plus to minus, right? Plus on VG2, minus on VG3. And then finally, V line 3, right? We're going VG3 to VG1. So look, there's the plus goes down to VG3, and then the minus goes back to VG1. You know, again, it's one of these habits, like I was saying with the generators. So you would just throw in V line 3 here and just have it, you know, plus on top, right? You just maybe cut and paste, right? 3 of these, bang, 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 and you don't even think about that. Well, if you get one of these backwards, you know, if this plus is up here, or you get one of the generators backwards, you know, the plus is up here, or the same thing out here, you put a voltmeter out here backwards, or maybe you have an ammeter in here and you got that reversed. Oh man, things can be ugly when you start going in. They're not going to make any sense. Okay, I'll show you an example of that once we conclude here. So what we should see, right, if you went through, like I said, the videos explaining how this all works, how you know, a line voltage works, you know that the fudge factor, so to speak, is the square root of 3, a little over 1.7, about 1.732. So our 120 volt RMS turns into approximately 208 volts RMS for a line voltage, right? So here's our little equation down here, right? The square root of 3, right? Okay, so that's the line versus the Y. And in this case, that's either the generator or the load because they're both, you know, they're both Y connections. All right? Okie dokie. Now, that turns into a peak voltage of just under 300 volts, 294 volts. So when I do the transient analysis, right, these line voltages should be showing up at just under 300 volts, and these 3 load voltages, these Y voltages, right, because again, here's our ground, they should be showing up at about 170 volts peak, just under. We should see 120 degrees phase shift between the 3 load voltages as well as the 3 line voltages. Now, between the load and the line, we should see about a 30-degree phase shift. Okay? Now, just to show you that, because this sometimes is a little confusing for people, just to show you that, I'm going to do a little quickie kind of drawing over here. So if you think about you know, what it means to say, like line voltage number 1, all right? We're saying it's, well, you know, voltage is always a difference, right? So that's VG1 minus VG2. Well, VG1 is a magnitude, you know, if you want to do a RMS, it's 120 volt magnitude out here at 0 degrees. And what's VG2? Well, it's also 120. It's the same magnitude length, right? But the angle now would be 120 degrees. So, you know, we come back, there's 90, 120's out here somewhere. All right, so you're like 30 degrees off of that vertical. All right, so you want to say, okay, what's this minus this? Well, trying to visualize a minus on a vector is a little tricky. It's easier, however, to just think in terms of adding the negative. So to negate this, to make this a negative, so I can just add it to this, right? What do? Well, you put a minus sign in front. It's like adding 180 degrees. So that 120 gets rotated out around to 300, right? So you got this, and 180 in opposition is out here. So you have a magnitude out here of 120, and you have magnitude over here of 120. So this is at 0. This is at 300, or minus 60 if you prefer. So the magnitudes are identical, which means that the resultant is going to have an angle in between those two. That's 0, that's minus 60, so we're looking at a 30-degree, negative 30-degree shift out here at some larger magnitude, right? That 120 turns into 208 RMS, right? Or 170 peak turns into just under 300 peak, all right? So that's what we have for that. Get rid of my little drawing here. Okay, so let's do a transient analysis on this. I am not going to throw in the excitation because the generator out here is going to be exactly the same. You can just follow the line out. It's going to be exactly the same as the load. So, you know, why be redundant? We'll be redundantly redundant. The Department of Redundancy department. All right, so look at all of these nice waveforms. I think we need a legend. Okay, so we got line 1, 2, 3. So let's go take a look at this, right? Lighten one of these. So that's V line number 1. And like I said, that should be just under 300 volts, which we can see it is. There's V line number 3. Okay, same amplitude. There's V line number 2, same amplitude. Without going through it, I think you can just eyeball this and say that these are equally spaced, that they're going to be 120 degrees apart. Then we can come down here. All right, so what are we looking at? Loads. So these are the 120 RMS, or about 170, right? So there's 150, 60, 70. So we can say, okay, that looks good. All right, there's our V load 3, V load 2. So this is looking good. Everything is you know, right amplitude, spacing is good. We can even go in and check the that 30-degree phase shift I was talking about, right? So if I take this, I'm just going to bring this down to right, well, I can't get it exact, but close enough. So let's just check these two, try to get them right around 0. All right, so we've got like 13 point, almost 1.4, 1.39 blah milliseconds of a time delay. And of course, a period, 1 over 60 hertz, is going to be 16.666666 milliseconds. So if you whip out your calculator and you put in 1.39, you know, whatever, you're going to get that 30 degrees that I was talking about. All right. Okay, so that looks good. We are clam happy, happy as a clam. All right, now, how happy are clams? I don't really know. But supposedly clams are happy. So I did say, all right, that if you messed up one of these phases, you're going to get some weird stuff. All right, so let's look at one that's bad. Okay, so it's the same circuit, except I inadvertently put this thing in back. Well, I purposely put it in backwards, but I'm just saying, you know, if you had just taken the 3 of them, like I said initially, and you just threw it down here and wired it up, okay, this thing is actually 180 degrees out of phase, okay, of what it should be. It should be 240, but it's actually 240. You could either think of it as plus 180 or minus 180. It won't make any difference. But this thing is actually sitting at an angle of like 60 degrees, okay? Burnt, not good. So when you simulate this, what ends up happening? You know, what do you see when we're all done? I mean, how weird is it? Let's find out. Wow, how crazy is this? You know, instead of having 3 of these large line voltages, I only see 1. Okay. As a matter of fact, if you look carefully, you'll notice that we're actually missing a waveform, and that's just because it's overlaying another one. There really are 6 of them. But we do see that there's 4 of these smaller ones. Okay, so this is really kind of goofy. You know, so there's line 1, and then we go through these small ones, and that's supposed to be line 2. What? You know, okay, there's load 2. This one is load 3, and that one's load 1. So, you know, that's all it took, just putting one of these in backwards, and you've got yourself a royal mess, right? So there's a gotcha. There's a gotcha. So it's not just a matter of getting the amplitudes right and the frequency and, you know, setting up the phase. You really do have to connect these together correctly. And even if you connected this together correctly, but you messed up what was going on out here, and you put one of these meters in backwards, or like I said, if you had an ammeter, you put that in backwards, the same kind of thing is going to happen. You're going to end up with some, you know, wacky looking thing, right? So my recommendation is, initially when you look at this, try doing the simplest thing, which is a wye. What we have here, a Y generator with a Y-connected load. Make sure that you've got this working, that you have the phases, you know, you have the 3 lines and you have the 3 loads, and everything is the right amplitude and everything is equally spaced. Then you're good to go. All right. So let's turn our attention now to a Y generator with a delta connected load. Okay, so here the interesting thing would really be the currents. Okay, we've already determined based on the preceding one that the line voltages, for the 120 volts that we have for the generators, the line voltages are going to work out to 208 volts. So I ripped those voltmeters out, and instead I put in some ammeters so we can see what the heck is going on over here. Okay. Of course, the delta, these resistors, these load resistors, see the line voltage rather than the generator voltage, all right, in this configuration. So whereas before there was sort of this one-to-one correspondence, so like this generator drove this resistor, okay, that's not really the case anymore. All right, so you would have known that it had 120 volts across that. Now, this thing is connected. R1 is actually connected between, the VG1 and VG3 terminals. All right. Okay. What ends up happening here is, if you did the computation, this is 208 volts RMS, or just under 300 volts peak. So when you divide that out, 10 ohms, you're going to get just about 30 amps. Okay, just about 30 amps of current. And of course, when we look at the line current, once again, that constant, that square root of 3, that 1.73 factor, shows up between line currents and load currents. So the line current is going to be roughly 1.7 times bigger than whatever that load current is. So you take that 30 amps, you multiply it by 1.73, and you're going to get 51, 52 amps, something like that. All right. All right, let's check the phases, because again, that's what we're interested in. We should see 3 currents, right? These 3 out here, these load currents, all sitting around 30 amps peak, and then 3 line currents. Again, it's going to be shifted, 1-to-1 by like 30 degrees from these guys to these guys, or these things to these things. Shouldn't call them guys. But again, 120 between the set, 120 between this set. All right. Okay, so once again, we'll do a transient analysis. Bingo. Hey, looks pretty good. All right, let's get our legend out here. So we'll come across, all right, there's line number 1, line number 3, line number 2, and the amplitudes look good, right? We were talking about a little over 50, so I can see there's 50 right there. That looks like a little over 50. They're evenly spaced, so there's 120 degrees. If I come down onto these, right, there's load 1, load 3, load 2. So that looks good. All right, back to our load 1. And again, if we look at the phase differential over here, just to be really complete about it, try to get that on the 0 cross, and then the nearest for the line. Those are pretty close. Okay, so we're getting about 1.39 milliseconds for that shift. Again, 16 2/3 milliseconds for the period. So again, that's going to work out to the 30 degrees, right? Like I said, you can get out your calculator and verify that, but that's looking good, right? We see everything that we expect to see. And like I said, we don't have a 3-phase generator. We just built it, right? So other thing I want to point out, we talked about the generator, but what about the load? I want you to look at the polarities for the ammeters. So the incoming line currents are kind of obvious, right? The currents coming, you kind of think of the currents coming out of the generator, even though it's AC, sort of a reference kind of thing. So it's plus to minus, plus to minus, plus to minus. No biggie there. But look what's going on here. All right, so this is like plus to minus, top to bottom. This is minus to plus, top to bottom. This is plus to minus, left to right. What's the sense in here? Again, think of a central point and go around clockwise. Minus to plus, right? Minus to plus, come around, minus to plus, come around, minus to plus. All right? If you are consistent with that, the phases are going to work out right. Right? So that's my recommendation. Those are sort of the gotchas that you're going to see on these wye-connected systems with the generator and a delta-connected load if you're looking at currents. Same kind of thing if I was interested in the voltages out here. right? You'd stick your voltmeter out here. So, you know, in the case of Tina, right, you know, we'd be grabbing these. And a different simulator, you might have, instead of this, you might have like a virtual DMM that you could hook up. But you would still have to follow those same polarity rules, okay? So there you go. Now, part 2, we're going to look at a delta-connected generator, and again, with the both Y and delta-connected load. And there's a couple of different gotchas there, right? There's a couple of different places that you might screw up that, you know, all depending. These things, however, you know, talking about the polarities, they're still there. You always have to keep those in mind. You start with the 3 generators, right? You come back here, you start with the 3 generators, and you make sure you have the right amplitudes, peak or RMS, because some simulators, you have a choice. They'll have a signal generator, which will be in peak, and they'll have a power generator, which will be RMS. So if you have a power generator, you're probably better off using that, right? So you can specify an RMS voltage. Otherwise, use peak like in Tina, and make sure you get the phases, okay? And then orient them correctly. Remember this little circular idea going around, all right? Plus, 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 okay? Great. Okay, so take care. We'll see you next time for part 2.